Suppose we have a random variable that can take on the values 1, 2, 3, all the way up to 9. And it takes on each of these values with equal probability. That is, there's an 11% chance that the random variable will take on the value 1. There's an 11% chance that it will take on the value 2. There's an 11% chance it will take on the value 3, and so on, all the way up through 9. We call this random variable uniformly distributed because the probability of it taking on each of these values is the same. So suppose we have 11,520 observations of this random variable. We can construct a histogram of the random variable, and the histogram shows us that the probability of it taking on each value is the same. The average, or the expected value, is the center point, in this case 5. And the standard deviation is the average distance the random variable wanders away from this center point, in this case 2.58. Now let's take these 11,520 observations and pair them up in groups of 2. And we'll take the average of each of these pairs of 2 observations. The first 2 observations average to 3. The next 2 observations average to 7. The next 2 observations average to 2.5. The next 2 observations average to 3. And we can continue in this fashion, averaging each of the pairs of observations. In total, we'll have 5,760 averages, each of which is the average of 2 observations of our uniformly distributed random variable. Now, let's build a histogram of these averages. And when we look at the histogram, something interesting emerges. While the individual observations were uniformly distributed, the averages of pairs of observations are no longer uniformly distributed. There's a low probability that our pairs of observations will average to 1. There's also a low probability that they'll average to 9. There's a much higher probability that they'll average to 5. Now, why is this so? Well, consider, we're averaging 2 observations. The only way to get an average of 1 is for both of those observations to be 1. Similarly, the only way to get an average of 9 is for both of those observations to be 9. But there are 5 ways that 2 observations can average to 5. You can have a 1 and a 9, this averages to 5. You can have a 2 and an 8, which also averages to 5. 3 and 7 averages to 5, as do 4 and 6 and 5 and 5. Because there are more ways to get an average of 5 and fewer ways to get averages of 4, 3, 2, and 1, as well as 6, 7, 8, and 9, our averages now have a peaked distribution. It's more likely that our average will be in the center around 5 and less likely that we'll find it at the ends toward 1 and 9. Notice something else. Our random variable isn't as spread out as it was before. The likelihood of the random variable wandering away from this center point of 5 is less. The tendency of an observation to wander away from the center point of a distribution is called the standard deviation. The tendency for a sample statistic, like an average, to wander away from the center of its distribution is called a standard error. A standard error is the standard deviation of a sample statistic. In this case, our sample statistic is a sample mean. It turns out that the standard error of a sample mean is the standard deviation of the observations that feed into the mean divided by the square root of the number of observations that feed into the mean. For example, we have 11,520 observations of a random variable. The standard deviation of these individual observations is 2.58. When we pair up these observations and calculate a bunch of averages, the standard error of these averages is 2.58 divided by the square root of 2, because each average is comprised of 2 observations. So notice what happens if we construct sample averages based on more observations. For example, if we take every 4 observations and average them together, we get 2,880 sample means. These sample means are distributed around the center point of 5, and the standard error of these sample means is 2.58 divided by the square root of 4, or 1.29. If we take our 11,520 observations and group them into sets of 8 and take the average of each set of 8, again we get a bunch of sample means. In this case, 1,440. These sample means are distributed around this center point of 5, and the standard error of these sample means is 2.58 divided by the square root of 8, or 0.91. Similarly, we can take groups of 20 observations. The 576 sample means, each of which is based on 20 observations, are distributed around this center point of 5 with a standard error of 2.58 divided by the square root of 20, or 0.58. So notice two things. Starting with a random variable that has some distribution, in this case a uniform distribution, we can take sample averages of groups of these observations. The larger the number of observations that feed into the sample averages, the lower is the standard error of the sample averages, and the more normally distributed the sample averages are. We call this result the central limit theorem. The central limit theorem says, regardless of the distribution of the underlying observations, when you take sample averages of these observations, the sample averages will tend to be normally distributed as the number of observations in each sample increases.